Hello and welcome to this Texas Instruments Australia tutorial for students, in particular students of QCE mathematical methods who are currently preparing for their external exams and using the TI-84 technology. Your presenter this evening will be Isabel Hoadley, and also fielding additional questions in the background will be Rodney Anderson. Good afternoon to you both.
Thank you, Brian. I'm really excited to be chatting to you for the next kind of half an hour or so about some of the questions that might come up in your exams towards the end of the year. So I picked out a selection of questions all from the sample paper from 2020 from the QCAA curriculum, and we're just going to talk through how we can best use the TI-84 technology to help you in answering those questions. So starting off, the first question we're looking at has a population of bacteria after T hours is given by this function, 5,000 e to the power of 0.18 t, and we're asked to find the rate of increase in this population at 15 minutes. So you're just going to have to bear with me. I'm going to be flicking a little bit between my PowerPoint and the calculator. So if I get my calculator up here, I've already put this equation in just to start us off nice and easily, but a couple of things we need to be wary about. First one is that we use E, not the letter E, the capital E, but we're using the Euler's E just here. And the other thing is that we're using the X variable as well, which we can find here. So if we put in this function, first thing we need to do is set up the window to make sure that we can actually see our graph. So the question called for finding the time at 15 minutes. So I'm actually going to keep my x min as 0 and my x max as 1 because our time variable was in hours. So that should be plenty of room there to be able to see that. The y min, I'm going to keep that as 0, but I'm going to put it all at the y max all the way up to 8,000, and that's because I had that 5,000 at the start of my question. So that would be where my exponential graph was starting from. So I'm expecting it to go a bit bigger than that, so I'm going to go for 8,000. I'm going to hit graph, and I can see there is the line depicting the population. So from here, to find the rate of increase, I'm looking for the derivative. So I'm going to go second, calc, number 6, which is now dy on dx. And sorry, pressed enter too quickly, number 6. And I'm looking for where my x was 0.25 or a quarter of an hour or 15 minutes. So I'm going to put that in there, and I can see that that ends up with dy on dx equals 941.42, which is equal to my answer D in that question. I just wanted to show you another way you can also do this question, and that's using just the calculator mode, just at the start, just the computing mode. So if I go alpha F2, you see I've got all these quick keys functions here. Now I'm looking for calculating my derivative, so I'm going to press number 3, typing x because I'm deriving with respect to x, and then I'm going to type in that same function that we had before. So 5,000 e to the power of that, because I'm pressing second and I shouldn't be, power of 0.18x. And again, I'm solving for where x is equal to 0.25. So if I hit enter there, I end up with that same value, and that's just another way that we can answer that same question. Moving on to the next one, we're looking for using the trapezoidal rule with 4 sections to approximate the area under the curve x squared plus 5. Between x equals 0 and x is 2. So this might seem like a question that you could probably pretty easily do by hand, but I actually think it's actually easier to do it on the calculator. I'm going to show you how again. So if we go into our list editor, so if I go into stats, into edit, I've got some lists here. So remember that we were breaking up our x value between 0 and 2 into 4 sections. So I'm going to use intervals of 0.5 and break that up so that I would have 4 rectangles or 4 trapeziums, I should say, to calculate my trapezoidal rule from 4. Now my equation was x squared plus 5. So now I'm going to input a rule. If I highlight the top of that list too, what I want to do is square my list 1 value, which remembering is our x value. I'm going to square that and add 5, so following that same rule as you're given in the question. And that comes out with our y values that we would expect from there. Now, I know that with the trapezoidal rule, I take our upper and our lower values have slightly less significance than the middle ones. So what I'm going to actually do is go across to list 3. And in list 3, I'm just going to retype just that first x value, or so the first y value, I should say, and the last y value. So the 5 and the 9. And in my list 4, I'm going to type in the 3 middle ones. So 5.25, 6, and 7.25 there. Now when I exit that, I'm going to use my formula for my trapezoidal rule. So my delta x was 0.5 over 2. And then I'm going to look at the sum of, so to get the sum of, we go second list across to the math menu, sorry, and we go down to number 5, and that gives us the sum. So I'm looking at the sum of my list 3, remembering that that was the first and the last y value, plus I'm going to take 2 times the sum of that list 4, and that adds together all of the values in the list 3 and the list 4 as per our trapezoidal rule. So I'm going to hit enter, and I end up with 12.75, and that, as we can see, B would be the correct answer there. Moving on to the next question, we're looking at the area of the region enclosed by the 2 graphs here. So x root x plus 1 and y equals 2x. So the first thing I'm going to do is just input those into my function editor up here. So if I head to y equals, now my first one was x square root, x plus 1. And my second one was just 2x. Now again, I need to set up my window. And in this case, I'm going to set it up from 0 to, I'm going to go with an x value of around about 6. And I'm going to set up from y to about, around about 8 from here. So I'm going to graph that. And if you're not sure what window you want to set up at, and if you want to just kind of check it out from -10 to 10 or something like that, just to check where you're starting off with first, if you head to Zoom and then go to Zoom Standard, I'll show you what that looks like. You can see that you get that function, and then from there you can start looking at where maybe you want to cut it off from. So again, I'm just going to change that back. So it was about 6 and 0 to 8. All right, so if we go back to the graph, the first thing that I want to do to calculate my area is to find where the point where those 2 functions intersect. So if I go second calc down to number 5 this time for the intersection point, I need to hit enter once on my first function, once on my second function, and then around about in the middle. And I can see there I have an intersection point where x equals 3 and y equals 6. From here, the next thing I'm going to do is I'm going to go in and actually, sorry, I'm just going to go back to the graph for a second, talk you through this. So as what I can see here is my y2 is actually my upper bound function. So if I was going to work this out from hand, I could find the area from 3 to 0 of my y2, or this red line here, and then I could subtract off the area of my lower bound function. There is actually an easier way to do it, and that's just to straight away go through and subtract the lower function from the upper one. So I can go in here, I'm going to use alpha F4 just to get up my variables really quickly, and I'm going to go y2, again, remembering that was the upper line, minus y1, which is the lower line, and this is going to give me a third graph, which is the difference between those 2 functions, and I can see there I've got an x-intercept at the same point where my intersection point was. From here, I can then calculate my area, and I just need to make sure that I'm on the right function. So this is currently on my blue function, I'm going to tab through, get to the black one. You can just do that using the up and down arrows there. My lower limit is 0. My upper limit is 3. And there's our area, 1.267, which corresponds to A as the correct answer for that question there. All right, moving on to some statistics. So we've got the birth mass of babies is normally distributed with a mean of 3,500 and a standard deviation of 500 grams. We're trying to find the probability that our birth mass would be less than 3,200. So I'm going to get out of here and I'm going to head into my distribution menu. So second vase gives me the distribution. In this case, I'm after my normal CDF because I'm looking at a less than value, less than 3,200. And anytime you've got an inequality, you're always using CDF. So that would be also true for greater than. You would still use CDF in that case, just not equal to. So my lower boundary is negative infinity, which comes up in the calculator as negative E99. That's the smallest possible value that we can have. My upper limit was 3,200 because I wanted to find anything that was lower than 3,200. So that would be my upper. My mean, 3,500, and a standard deviation of 500 grams. I'm going to paste that in. And there we go. I can see that my probability there that of having a baby less than 3,200 would be 2742. Which is there, 27 as the correct answer for D. Okay, again, more statistics. So question number 10 is a confidence interval question. And it's a binomial confidence interval. I can tell that because we're talking about people having tertiary qualifications. So that's they either have it or they don't. It's not something that we're measuring. So we're using a binomial distribution here. So we've got 142 out of 200 people have tertiary qualifications, and we want to find what our 95% confidence interval for that would be. So to get to our confidence intervals, we use the stat menu. We're going to go across to tests, and like I said, this is a binomial confidence interval question. So that's actually kind of towards the bottom of our menu. So if I scroll down, you can also scroll up to find it if you like as well, but if I scroll down, I'm going to use this one proportional Z interval. Okay, so that's for our binomial. So we're going to go into here. Now, my X value was 142 out of a total 200 people. And again, I was looking for the 95% confidence interval. So I'm going to calculate that. And we end up with 0.647, which I think rounds to 0.65 in the question, and then 0.77. So we can see that 0.65, 0.77. So in this case, C would be our correct answer. All right, on to some extended response. So from here, we're told that people with type O negative blood are said to be universal donors. And in Australia, 9% of the population have this type of blood. On a given day, we're going to, a random group of 45 people are donating blood. So we're going to skip over part A because this is an interpretation question. That's fairly straightforward. What we're wanting to focus on is what the calculator can do. So I hope you don't mind. We're going to move past that one. We will go through calculating the mean and the standard deviation though. So our mean is, if we go out of here, okay, so we should know that our mean is our sample size, so 45, n times by the probability of that occurring, so 0.09, which gives us 4.05, and our standard deviation, we're going to multiply that again by our inverse probability, so 1 minus 0.09, and then this gives us 3.6855. This is our variance. So the last thing we need to do is take the square root of that answer, and we end up with 1.9197. Now, quite often with statistics, you need to round things to 4 decimal places. So a quick, easy way you can round to 4 decimal places, head to the math menu, scroll across to number. If we go to round, again, we're going to take that answer, so second, and then the negative sign gives you that answer, copy down, comma 4 for 4 decimal places, and then enter, and that would round that number. You know, if we're feeling lazy and we don't want to round it ourselves, there we go. There it is, rounded to 4 decimal places. And perfect. I just got to check the second half of that question. So that's the mean and the standard deviation. The next part of the question, we want to determine the probability that no more than 3 of the donors are universal donors. So if we're talking about no more than 3, that means we're looking at whether there's 0, 1, 2, or 3. So this is again, it's a less than probability. We're finding the value that we're finding the probability that X would be less than or equal to 3. So again, I'm going to head to my distribution. And this is not a normal distribution this time. We're looking for a binomial distribution. And again, cumulative because we've got that less than value. So if I head into binom CDF, I have my trials 45 altogether. My probability is 0.09. I'm looking for an X value less than 3, so my X value is 3. And I'm going to paste that in, and there we can see the probability is 0.4147. Again, if I wanted to round that to 4 decimal places, I could just do my sneaky little rounding trick like I did before. In fact, I could even, I think, copy that down, and it'll do it for me there. So I don't even need to type it in again if I don't want to. All right, moving on. That's our 5 marks done. Question 17 is worth 3 marks. So we're given the rate at which some pollution is going into a lake every 6 days. So I'm going to type this into my list, again on my calculator. But first thing I need to do with that data is make sure I've got my list cleared. Now, the way I like to clear my lists is I head to the stat menu. I'm going to go to clear list. And then if I use the list functions down the bottom, so list 1, comma, list 2, comma, list 3, comma, list 4, that's going to clear all those lists for me. So now when I go back into my stat editor, they're all nice and clear. So my data was 0, 6, 12, 18, 24, and 30 days. And then in my list 2, I had 7, 8, 10, 13, 17, and 22 as my rate of my pollution heading into the lake. So from here, we're told in our question that this information can be modeled as a quadratic. So I want to find the equation of that quadratic. So to do that, I'm going to use my quadratic regression. So if I head to stat, across to calc, down to number 5, which is a quadratic regression, I'm going to keep my X list as list 1, my Y list as list 2. I'm happy with that. That's my time variable and the pollution. But in this store reg EQ, it's really handy if you type in alpha F4 and put in your Y1. And what that'll do is it will automatically take the equation that you come up with and put that straight into your Y1 so that it's ready to use in the graphing screen. So I'm going to calculate that. And here I can see my 3 values here, my 3 constants. And I can also see that I've got an R² value of 1. So that's a pretty handy thing to have highlighted on the calculator, just in case you typed in a number wrong or something. We were told that it could model as a quadratic, so we're expecting a pretty high R value. So if you had, something that was quite low, probably you've maybe hit the wrong button or you've typed in something incorrectly. If I just show you that you do actually have that. So when I go into Y1, here we go. We can see that equation's in there. I'm just going to get rid of Y2 and Y3. Again, I need to set up my window. Now my table here, my highest X value was 30 and my highest Y value was 22. But I'm going to make it go a little bit more than that. So I'm going to go to 35 and to a maximum of, we'll say 30. I'm going to graph that. And here we go. I can see my quadratic. Now I haven't quite finished the question, because it's asking me to determine the total amount of the pollution entering the lake in that period. So that's our integral of the rate. So from here, I'm going to go second, calc. I'm going to go scroll down to number 7, which is my integral. My lower limit is 0. My upper limit is 30 because that's our maximum number of days we were looking at. And we can see here that we end up with 372.5 units of pollution in total in the lake over those 30 days. There we go. I love this question. I thought it was a really good, interesting question to put in the exam, and there's a lot of stuff with technology that you can do to answer it. So getting stuck in here, I'm just going to input before we kind of talk through it, I'm just going to put in this equation. So ln 5x plus e minus 1. Perfect. So there's my equation. Okay, so this question, we're told a couple of things. The first thing is we've got this farmer. He has a paddock which has a boundary of a creek and also two fences, fence A and fence B. Fence B is 4 kilometres long, but we don't know what X value that is. And fence A spans along this bottom side here. What he wants to do is he wants to divide this paddock with half the area. So he wants to put in a third fence, call that fence C, somewhere so that the area between the two paddocks is the same. The creek has this equation, ln 5x plus e minus 1. So the first thing that I want to find is where is fence B. So fence B is where it's 4 kilometres long, so it's where we've got a y value of 4. So when I head to my window, I'm going to go x max. I'm going to make my x value around about 60 again, or actually we'll go 50. And again, I've done this question before, but I had to play around with it a little bit at the start. So it might take you a while to find exactly what windows you need to use. Don't be scared to play around with it if you need to. And I'm going to make my y max 5, and that's because I want to find where my intersection point at 4 was. Okay, so here's the graph. Here's our intersection point. Again, we're going to calculate that. So number 5, intersect once on the first curve, once on the second curve, once in the middle, and I can see there I get an x value 29.1389. Now, something really neat that you can do is head out of here, press answer in your main screen and enter, and that actually copies down the answer that you found from your graph. So I'm going to store that as variable A in my calculator. And what that means is every time I type A, it recognizes it as that number. Heading back to my graph, the next thing that I want to find is what is the area under the blue graph, because we want to find half of that. So I'm going to calculate my integral from 0 to A, because that was that x value for the intersect that we found. And we can see that there, and that's my area, 89.59. Again, I'm going to store that a second time. So second, quit, I'm going to head out of there. I'm going to hit answer again, enter. That comes up with that value. And to store the variable, we're going to go press that store button there that has the arrow, and then I'm going to type in the letter B. There it is again. Okay, from here, we're actually wanting to find what half the area is. So I'm going to divide that by 2. And I'm going to store a third variable, C. Store that value. Enter. Okay, now, the next thing we're going to do with this question is I'm going to head back to my y equals screen. And this is maybe something that a lot of people haven't maybe done before, but we can actually plot the integral function of our y1. So to get to that integral function, we go alpha f2, and I think it's number 4. And what we're going to plot is our area from an upper value of x to a lower value of 0. And we're going to take the integral of that y1. So I'm going to go alpha f4 y1. I'm integrating with respect to x. And the last thing is I want to find where that's equal to that half area which we stored under the letter C. So I'm also going to put in 4 for y4, which is at C, and I'm going to find the intersection point between those two functions there. Now, you are going to have to bear with me a little bit. This is a little bit slow when it comes to graphing. I'm also going to change my y max up to 50. because I know that area that we wanted to find was at about 45. So I need to take that into account on the screen. So I'm going to go to graph. Now, when you're in your exams and you're doing this, I mean, it is worthwhile, I think, being able to graph it, even though it does take quite a long time. And that's because what your graph's doing is it's integrating absolutely every single value of your function. So it does take a lot of computing, and the TI-84 is an excellent calculator, but it's also not, it's not just it's meant to be for taking around, so it doesn't have a huge, fast computing power in it, and that's fine because it does everything that we want it to do. So you'll see here, this little yellow thing is up here, spinning around. And when that's done, we'll know that that's finished. I should also mention as well, this question's worth 5 marks. So even though you can do all of this on your calculator, you should show all of your knowledge and all of your working in your paper. So you should kind of have at least 5 things that you need to show. So every time you do an integral calculation, you should write that down on your paper and make sure you're showing really clearly to the examiners that you know what you're doing and that everything's coming along nicely. We'll just wait for just another couple of seconds just for this to finish going. And I know it'll be finished as well because we'll get that nice pink line through C, which was the Y3 there, the Y4 there that we put in as well. Perfect. There we go. Awesome. So thank you for bearing with me. I would suggest if you're doing this in an exam, obviously maybe put it in and then jump back and do a different question and come back to it. So anytime when you're sketching a derivative graph or an integral graph, it does take a long time. So we want to find that intersection point. So I'm going to go second, calc, down to my intersect. And again, press once on the first curve, once on the second curve, and then we can move that cursor into the middle, around about, guess where we think the intersection point is. And again, because it's calculating with the integral, it will take a little bit longer than it normally does. So again, still thinking there. And we can see there we get an intersection point at 17.24, which we then could store that value and we could check it's half, but it definitely is half, and we will move on to the next question. Cool. Okay, so question 15, again, we're back to some statistics. So we've got a proportion of Australians who support the removal of single-use plastic bags is 64%. So we're using a normal approximation to the binomial. This is obviously binomial because you're either supporting single-use plastic bags or you're not. And we have a sample size of 100. And we want to determine the probability that more than 70% of those surveyed support the removal of single-use plastic bags. So the first thing that we're going to need to find is what is the mean and the standard deviation of our sample. So our mean, because we're using normal approximation to the binomial, our mean is just the same as our population proportion. So 0.64, and I'm going to store that again. We'll use M for mean, so I'm going to store that under mean. And I'm going to work out my standard deviation, which is the mean, so alpha M times by 1 minus M. So again, the inverse of our proportion. And I could have done that as 0.36, but it's nice to use the variables again. 1 minus M over our N value. Now, there was 100 people in our population. So this gives us our variance. We take the square root of that answer, and we end up with our standard deviation. I'm going to store that under, we'll go with S for standard deviation. And the reason why I'm storing those values is because now when it comes into calculating our normal CDF, to find that probability of more than 70%, my lower limit, more than 70%, so 0.7, upper limit, I'm looking for E99, too many letters, E99. My mean, I can just type that in as M, and my standard deviation, I can just type that in as S. Okay, so I'm wanting to paste that. There we go. And we can see that our probability is 0.1064. There we go. The second part of this question, we're determining a size of the sample for the survey to achieve a margin of error of 4%. Now, this is a bit of algebraic working. I've done it already over here on the side. So we're solving for n to find the size of our sample, which is 553. Which is 553. And if we wanted to, I thought I'd show you here as well. Actually, we'll do this in the calculator. So if I head into stat, across into tests, and in this case, we've got a normal distribution confidence interval that we're working with. So if I go to Z interval, that's my normal distribution confidence interval function. Remember, we use one prop Z interval for the binomial one. I'm going to use stats. Again, my standard deviation was, I put that in as S. My mean of X, my X bar, I put that in as M. N was equal to 500 and, I think it was 533 or 553? 553. And I'm calculating the 95% confidence interval. I calculate that. There's my two values. If I subtract the lower one from the upper one, I should expect around about 0.08 as my width between the interval, which means we've got a margin of confidence of 0.04 on either side. Okay, so that's just how you can double check your answer using that Z interval. We're going to skip over C because that's pretty much the same as B. I don't think we need to go over that again. Again, you're solving, and then you could use the Z interval to check your answer if you wanted to. And D, determine the probability that in a randomly selected sample of size 25, the sample proportion is equal to the population proportion. So in this case, we're going back to binomial because we're wanting to work with a sample size of 25. So from here, I'm going to go into my binomial distribution, and we're looking at where it's equal to. So I'm going to binomial PDF where we've got an equal to, not CDF where we had either a greater than or a less than value. So my trials were 25 in this case. My probability is still 0.64, okay, my population proportion. Now my X value I was trying to find was the same as the population proportion. So I'm going to times 25 by 0.64, so 64% of 25. Paste that in there, and that will work it out for us. So we've got 0.1643. Very last question for this evening. Sorry, we are a little bit over time. I'll be really quick. I just wanted to use this last question just in terms of window setup, how you can use your equations to help you guide what your windows should be. So the scenario here is that we're looking at comparing daylight between Oslo and Brisbane. So I'm going to type in here, but to find where I'd actually, there we go. Sorry, I thought I wrote down my equations, but I didn't. So I've got 1.73, back to my calculator, 1.73 cos, and I believe it's pi x over 183. There. Okay. Plus 12.13. Okay, so this is modelling our sunlight in Brisbane. So from here, I just want to double check that I've got all that in there. Yep, perfect, lovely. So from here, if I want to set up my window for this function, I know I've got an amplitude of 1.73, I've got a Y translation of 12.13, and I've got a period change of pi on 183. So in my window, my x min, I'm going to keep that as 0. My x max, I know that my period is going to change in 2 pi over b. So I can type this in as 2 pi over that b value, which was pi over 183. And this will automatically chuck this into the graph for us. We don't need to work that out. So we end up with 366, as you can see there. Now my y min, my amplitude was 1.73. My y shift was 12.13. Now I'm going to go minus 1.73, taking away the amplitude. And likewise, the next one, 12.13 plus 1.73 for my amplitude in my other direction. And again, so that should nicely set up our window there. So when I head to graph, we should really nicely see that function there. So that's just how you can use what the equation actually is to inform your graph. And don't be scared of putting equations into the window. It's really easy and it makes it really nice to follow. All right, I think we will leave it there because most of these other things we've done, finding points of intersection, we might just we'll do part A quickly here. So determining the maximum number of hours because we didn't look at doing a maximum. I'm just going to do the maximum. I'm actually just going to set up this window a little bit towards the left a little bit, just so we can find that maximum and see the peak really nicely. So if I go back into the graph, we can see that there. We've just got a little bit more room to play around with there, even though it's not a lot. I apologise for that. So to find the maximum, we're going to go second, calc. We're going to use our maximum, number 4. Okay, we're just going to move this slightly to the left of that peak, slightly to the right of the peak, round about in the middle again. And we can see there we get a Y value of 13.86. So that would be our maximum number of hours of sunlight. All right, thank you very much for coming along tonight. And I hope you've learned at least something that you can take away and use in your exams. Awesome. Thank you.